Today we start one important topics. We start a important theorem. We now write now statement of this theorem. Let T belongs to BH, bounded linear operator from H to H, to be self-adjoint, that means adjoint of T equal to T. Then first let lambda equal to infimum of norm of x equal to 1 txx, inner product of txx, and if an x0 there exists and x0 belongs to H such that norm of x0 equal to 1 and lambda equal to inner product of tx0 x0, then lambda is an eigenvalue, then lambda be an eigenvalue of T with corresponding eigenvector x0. Okay, now we also write next part. Let mu equal to supremum of norm x equal to 1 inner product of txx if there exists an xa1 belongs to H such that mu equal to inner product of tx1 x1, then mu is an eigenvalue, of T with corresponding eigenvector x1, Okay, now we also going to prove of this theorem. First we write here proof, then marked as 1. Let alpha belongs to C and V belongs to H. By definition of lambda, we have T of x0 plus alpha v, here x0 plus alpha v greater than equal to lambda x0 plus alpha v, here x0 plus alpha v. Then we obtain from here tx0 x0 plus alpha conjugate tv alpha conjugate tv x0, okay, and alpha conjugate tx0v, then norm alpha conjugate norm of tv, okay, sorry, norm of tv here v, then this greater than equal to lambda their x0 inner product plus lambda alpha vx0 plus lambda alpha x0v alpha conjugate x0v, then lambda alpha conjugate vv. Okay, then next this implies that t of x0 plus here alpha x0 t, if t is self-adjoint, then here we write vtx0, and here alpha conjugate we write tx0v. Here norm alpha square we write here tvv. Okay, then this greater than equal to lambda x0, here lambda alpha x0v conjugate, here lambda alpha conjugate x0v, here lambda norm alpha square vv. Okay, then we erase our portion. Okay, we erase our portion. Then what we find? We find that here t of x0 plus alpha tx0v conjugate plus alpha conjugate tx0v plus norm of alpha square tvv greater than equal to lambda x0 inner product lambda alpha x0v conjugate lambda alpha conjugate x0v, then lambda alpha square vv inner product. Okay, then we erase lower portion and going to forward discussion about that. Okay, then what we get? Hence t of x0 inner product plus here 2 alpha real of tx0v, here norm alpha square tvv. Okay, greater than equal to lambda x0 plus lambda alpha square vv, here plus 2 of real alpha lambda, 2 of real alpha lambda, here x0v inner product. Okay, then what we obtain next? There is some problem here. Oh, now this one is okay. Oh, again some problem. Okay, then we start about that. Hence this one is happen. Okay, now we're going to forward. Then what we obtain? We obtain substitute lambda equal to tx0 x0 of inner product, and taking here alpha equal to r inner product of v t minus lambda I x0 conjugate, and r belongs to r. Then we conclude that here v t lambda I x0 equal to 0. Okay, for each v belongs to h, then t of x0 equal to lambda x0. Okay, then we're going to prove of another one. How we getting this one? Just taking minus t in place of t, and we also getting this second proof. Okay, so now we erase this portion and going to another theorem. Okay, erase this whole portion and going to another theorem. Okay, we write this theorem here. If t belongs to bounded linear operator from H to H is compact and self-adjoint, and self-adjoint, then at least one of the numbers is an eigenvalue. Then at least one of the number norm t or minus norm t is an eigenvalue. Okay, then we proceed this theorem. Obviously, by previous theorem we get there exists a sequence x in subset of h with norm of xn equal to 1 for Eigen such that lambda belongs to R and norm of xn converges to lambda where lambda equal to plus norm t or lambda equal to minus norm t. Okay, now then we write now what happened here. Norm of txn difference lambda xn square equal to here inner product of txn lambda xn lambda xn. This implies txn difference txn here lambda xn difference lambda xn txn plus lambda conjugate xn. Okay, then this one norm of txn square difference here this one is lambda txn a and lambda txn axn and here also lambda xn txn here lambda square norm xn square. Okay, since t is self-adjoint, so norm of txn square plus norm of lambda square xn square. Okay, norm of xn square. Here t is self-adjoint, so lambda and lambda conjugate. This one obviously difference lambda x txn xn. Here this one obviously txn xn. This one self-adjoint, and then what we get here 2 lambda square difference 2 lambda norm of txn xn. Okay, now lambda equal to norm of t, so this one is 2 less than equal to this one less than equal to this. Okay, then what we obtain, that since t is compact, we write here since t is compact and there exists a subsequence t to txnj of txn such that txnj converges to y. Okay, So Tx and J converge to C and J. Okay. So this implies Tx and J difference lambda C lambda x and J converge to 0 as n tending to infinity. Tx and J difference lambda x and J converge to 0 here as n tending to infinity. So we erase this portion. Then what we write here that is x and j converge to 1 by lambda y. Okay, hence what happened, hence y equal to limit nj tends to infinity t of x and j equal to 1 by lambda t of y. Hence lambda is an eigenvalue. Hence lambda be an eigenvalue. Okay, this implies ty equal to lambda y, so lambda be an eigenvalue. Now we prove this one also. So we discuss two important theorem today. Next here some corollary, also write some corollary about this theorem. If T belongs to compact operator from H to H, be self-adjoint, then maximum of norm x equal to 1, norm of Tx equal to norm of T. Okay, then we also going to another example. Here we write, let k such that L to 0 1 integral functions on 0 1 to L to 0 1 be defined by kft equal to 0 to t fs ts, then k is non-self-adjoint, okay, compact and does not possesses eigenvalue eigenvalues. So we also discussed that portions. Now we also going to another definition of invariant. Okay, we write definition here. Let a closed subspace M, a closed subspace M of H is said to be invariant under T, invariant under T belongs to bounded operator from H to H if and only if Tm subset of M, if both M and M perpendicular are invariant under T, are invariant under T, then we say that M is a reducing subspace for T. M is a reducing subspace for T. Okay. Then we also write here, if M is invariant under T, M is invariant under T if and only if M perpendicular is invariant under adjoint of T, under adjoint of T. Okay. Now we also write another result. Let T belongs to bounded linear operator from H to H. Let M be a closed subspace of a Hilbert space and PH to H be an orthogonal projection such that Rp equal to M, then range of then first one, M is invariant under T, M is invariant under T if and only if Tp equal to Ptp. Okay. Second, M reduces T if and only if Pt equal to Tp. Okay. Then we're going to some observation about this. We write this result and now going to some observation. Okay, observation. first we write if t is a self-adjoint operator, then every invariant subspace is reducing. Then every invariant subspace is reducing. Okay, and next we discuss about every eigenspace corresponding to a particular eigenvalue corresponding to a particular eigenvalue is invariant under the operator Okay, then the operator is self-adjoint. We erase our portion and we write here the operator is self-adjoint. The operator be self-adjoint is every eigenspace reduce the operator. Every eigenspace reduce the operator. Okay, then we write note. We also erase that portion. I write some note. Okay. If t be compact operator, and M is a closed subspace of H, M be a closed subspace of H, then the restriction operator is also compact. Then the restriction operator T restricted to M is also compact. Okay, then we stop here.